Pleasure to have Professor Nadia Zakamska giving the Astro Seminar today. She's a professor and vice chair of academics at Johns Hopkins University. She received her PhD in astrophysics from Princeton University. Before joining Johns Hopkins, she held a NASA Spitzer Fellowship and a John N. Bachal Fellowship at the Institute for Advanced Study, as well as a Carvey Fellowship at Stanford. Today, she'll be talking about James Webb Space Telescope breakthroughs in galaxy formation.
Okay, thank you so much for having me. And when I was talking about this with Anthony, I made a prediction that there was going to be 3 people, and I would be thrilled to see the 3 people in the audience the week of Thanksgiving. So thank you all. I really appreciate I appreciate you all being here, and I hope I can entertain you with some beautiful images and some interesting stories that have come out of JWST observations so far. So my So this is my situation for the last several years in terms of my research directions. Several years ago, I got really excited about various things in galactic astrophysics. So I started working on galactic variability surveys on stellar binaries of all kinds. We have some very interesting projects looking for ultra-compact binaries of compact remnants and on searching for progenitors of type 1a supernovae. So I would be very excited to talk to any of you about these topics. But much of my career I have spent in extragalactic astrophysics, working on galaxy formation, quasar feedback, extreme galactic winds. And so today, I'm here today to give you an update of what's been happening in extragalactic astrophysics with Webb. It's been kind of crazy. And so as I was writing this talk, I had real difficulty just kind of trying to zero in on a few choice topics to highlight here today, because it's been an incredibly dynamic area with a huge number of developments. And so maybe I'll try to give you a feeling for what's been happening. So I will remind everybody what we thought JWST was going to be like before the launch. Everybody had said for years it was going to be amazing. So let's remember why it was supposed to be amazing, all the technical and astrophysical reasons. And then I will highlight a couple of case studies that are going on in my group. So I'm working on understanding feeding and feedback of quasars at cosmic noon and on the physics and astrophysics of super Eddington quasars. And then we are also searching for dual quasars. So those are quasars that are very close together that are progenitors of binary supermassive black holes. But I also wanted, if we have time, to touch upon what are some of the big new questions that arose from the first 2 years of observations of JWST. So hopefully I'll just give you a quick tour of these big picture questions that are not necessarily my group's work. Okay, so the James Webb launched December 25th, 2001 from the French Guiana, European site in French Guiana. And it took a month to get to its location at the Lagrange 2 point of the Sun-Earth system. So the top figure is the view from above. Nothing is to scale, but you see the sun, you see the Earth, and you see James Webb on the far right of the image, and the picture below is the view edge-on. So now we are in the plane of the Sun-Earth orbital system, and you can see the trajectory of James Webb, and you can see L2 over here, and you see that it's on this wide sort of circular trajectory. Okay, so what is L2? L2 is a point where a particle experiences basically zero net force in this in the system co-rotating with the Sun-Earth system. Why is that important? Because James Webb is a propellant-limited telescope. So its lifetime is limited by how much propellant they could throw up with it into the orbit, because it needs to point, right? It needs to slew to objects. And so it's actually performing better than expected. That's why you may remember the expected lifetime of James Webb has been increasing because they first said, okay, 5 years, then they said 10 years. Now they're saying 20 years potentially, okay? And so that is because it's actually doing very well on its orbit. It's a very quiescent orbit that doesn't take a huge amount of effort to have it there, okay? So also in the first month, it deployed all its hardware. So let me show you this 1.5-minute video. So of course it launched the most compact possible configuration, and it's finite space of the rocket. Then it starts unfolding. Clock in the bottom right corner. Here we are 7 days after the launch, and it's halfway around space. Really incredible engineering. Okay, so then for months 2 to 4, there is optics alignment, cooling of the mid-infrared telescope down to 6 Kelvin, and this was the first photons from the telescope. So it's a bright star that they're trying to observe. And so now you're seeing 18 potato-sized images from 18 unfocused segments. Okay, and so they take a couple of months to bring it all together to this image, which we'll discuss also in a moment. So then months 5 and 6, calibration, commissioning, first science photons. So now we start seeing some of the things we will discuss again, which is that the difference in the diameter from, let's say, Spitzer Space Telescope, about a factor of 10, makes a difference for spatial resolution and sensitivity that we can detect. This is the same part of the Large Magellanic Cloud taken at 8 microns with 2 different facilities. Some of you might remember this. This was the first image shown by President Biden at the press conference on July 11th, and that's the day when the archive was also opened for anybody to use the previous month's worth of commissioning data. The first paper appeared on Archive 3 days later, led by the University of Arizona group. Max Pascali is a graduate student with Brenda Fry. And it was a really interesting paper. They identified, so this is a cluster of galaxies, strongly lensing background galaxies. And in this very first paper, they presented the catalog of all the multiply imaged background galaxies, which is the first necessary step to reconstruct the lensing potential of this cluster. Okay, and then our group got our first data 4 days later. We had no proprietary period.
It is my professional opinion that now is the time to panic.
That was our situation in July 2022. You can ask me about the proprietary period thing later. I don't want to get into it right now. I'm still suffering from PTSD a little bit. So maybe you've already seen this 50 times, and if so, I apologize, maybe not. I mean, I tend to be really embedded in JWST stuff because Space Telescope Science Institute that operates the instruments, right? So all the software does all of the scheduling for James Webb. is of course hosted on our campus. It's right across the street from our building. And so we tend to hear and see a lot about JWST. This thing says, "Go Webb, go! The hidden universe awakes." Okay, so what was so hidden about it? So we've already covered this. The changes in the diameter of the telescope are the two things. One is just the collecting area, which makes it more sensitive to faint objects, and another thing is the spatial resolution. So this bottom figure is the point spread function of the telescope, which demonstrates that it is at the limit available to us due to the diffraction of light. So you see this inverse Fourier transform of all the apertures, in particular, you see these dark rings, which you would have seen in a circular aperture too. And so the angular size of the core is lambda over d, inversely proportional to d, which is why the images with Webb are so much sharper than the previous generations. The instruments are also, in some sense, groundbreaking. So there's imaging spectroscopy, but my group uses a lot this mode called integral field spectroscopy, which gets you a spectrum at every point of an image. Unfortunately, that comes at the expense of the field of view, so it's a very small image. But that's one of the main modes in which we use James Webb. Okay, so let me show you just again one of the early data results as to what the spatial resolution and the sensitivity does for us. This is another strongly lensing cluster of galaxies, and it's blinking between the Hubble images and the Webb images, and there's this triply lensed redshift 11 galaxy, which is just a blob of red pixels in the Hubble image, and then it just kind of shows up as an actual real galaxy, actually a binary galaxy, so to speak, in the Webb images. So it's really quite transformational in these two respects. Okay, for astrophysics, okay, the coverage is from 1 to 25 microns, so it's infrared as compared to UV optical on Hubble. From the ground, we really cannot see much of anything above 2.5 microns, just the thermal emission from the atmosphere itself. And so that is transformative for cosmology for two reasons. So we have here a sequence of quasar spectra from redshift 5.7 to 6.4. So of course you see the emission moving, Lyman alpha moving towards near infrared. But you also see this really deep intergalactic absorption on the left side of Lyman alpha. So these objects are completely dark in the optical, you cannot see them. And so basically you cannot probe high redshift universe from the optical at all. And then due to the atmosphere, it's quite challenging to impossible to study objects at redshifts greater than 7. And Hubble, the reddest band they have is at 1.6 microns. And so once things redshift out of that band, it's impossible to do them with Hubble, no matter what the exposure time either. So what does this allow us to do? So this is the brief cosmic history as a function of time and redshift. So from early universe on the right to late universe to the left. So James Webb was primarily built to discover objects between reionization and cosmic dawn. So redshift 10 to 20 is the prime science of James Webb for the reasons that I just described. But in addition, for cosmic noon galaxies about redshift 2, 10 billion years ago, all of our standard diagnostics of rest frame optical emission of these galaxies, everything we know physically about these galaxies, their abundances, the sources of ionization, density of gas, temperature, everything moves into the infrared. And so, yes, it is possible to do this from the ground on the largest telescopes given arbitrary long exposure time, but that's not the ideal way to do it. And there are, of course, limitations. And so finally, cosmic dust tends to be much more opaque in the optical, more transparent in the infrared. So that makes a transformative difference for studying things at low redshifts and in our own galaxy. So this is a star forming region in our own galaxy. There's diffuse dust everywhere here that's blocking background stars. And once we go into the infrared, you can see that all of these stars pop up and you can see them. And so, and finally, of course, in the infrared, there's some particular atomic, molecular, and solid lattice transitions that cannot be seen from the ground. And so that enables a bunch of science for us because we can see phases of the medium that we cannot see from the ground, but it's also very relevant for studies of exoplanet atmospheres. So this is a quantum mechanical limitation, just where the transitions happen to be. Okay, so there are lots of great technical and astrophysical reasons why James Webb was supposed to be amazing, and I've already showed you some amazing images, but so let me tell you a few specific science cases. So this is case one. This is something my group has been working on for a long time, studying feeding and feedback of quasars at cosmic noon. Okay, so let's step back a little bit and talk about one of the big puzzles in galaxy formation is the shape of the galaxy luminosity function. So this is shown over here. So massive galaxies are on the right, low mass galaxies are on the left. And you can see that there's a particular, so the vertical axis is the number count. And so there's a bunch of small galaxies. Then there is a break in this distribution, which is actually where the Milky Way is. And then the number density drops like a rock. If you wrote down the simplest possible cosmological model, if you said, okay, let all baryons turn into stars, everything, all available baryons turn into stars, you get this line. Okay, so clearly something is very, very different. So the overall normalization is different. And so many of you will have heard this as a missing baryons problem. So meaning that not all baryons or only a fraction of baryons actually get converted to stars. You've all heard of the missing satellites problem probably, which is that the basic theory predicts a lot of small galaxies that we're seeing some of them, but not nearly enough. And then there's also a cutoff or a very steeply declining number counts here, which tells us that there's basically a maximum mass of galaxies in the universe. And so all of these, so galaxy formation theory has been working for decades now to try to reconcile all of these things and put together a systematic model that would explain all of those observations. We have various other observables. You may have heard of the M-sigma relation, which is the correlation between the black hole mass and the velocity dispersion of the host galaxy, which is surprising because the black hole is tiny compared to the galaxy, so it should have no dynamical influence on it. There's also this cosmic history of black hole and star formation rate density of the universe, which are very, very similar and very peculiar, right? So this shows the number density of luminous, powerful, supermassive black holes as a function of redshift. So they, they rose in numbers, and they drop like a rock towards the present day. And so this epoch of about redshift 2, so this was about 10 gigayears ago, is called cosmic noon, the peak epoch of quasar activity, and it's also the peak epoch of star formation rate density. And so galaxy formation theory should explain all of these different observations somehow. And so there's a very technical point here, which was clarified in this April 1st paper by Hopkins et al., who sought to put order to all of these cosmic noon, low redshift, high redshift, right? So they introduced formally, cleared up all the notations, and now we have high redshift, very high redshift, ultra high redshift, exceptionally high redshift, ludicrously high redshift. And then we have, cosmic noon, cosmic morning, cosmic dawn. And so then we have cosmic breakfast and maybe second breakfast. And so I'm very grateful to these people for doing all the hard work for cleaning up the nomenclature of the field, which we can now use, especially in James Webb era, where these words, are now very, very relevant. So I'm going to just use these words. Okay, so cosmic noon and cosmic brunch are my...
Makes sense to like -3.
Yeah, they're looking into the future. Yeah. Let's not go into, yeah, it's a little bit scary when you think about that. One of the key ingredients of modern galaxy formation theory is the so-called quasar feedback. Okay, so one way to sort of produce a plot like this, for example, is to reheat the gas that is available in the halo, or like literally throw it out of the galaxy and prevent it from forming stars. So that's the concept of the feedback, is something that prevents new stars from forming. And so supermassive black holes can do it. And one of the pathways in which they can do it is via launching galactic scale winds. And so this is a numerical simulation of a quasar-driven wind in a disk galaxy. It's a pretty rudimentary simulation. And there is a reason I'm showing this, because it captures one essential piece of physics that I want to illustrate. So the galaxy is edge-on like this. And you should imagine that there's a symmetric thing on the other side, right? So they're just showing us the half of the galaxy. And so it's a disk galaxy, and they launch outflows, and they actually launch outflows into this galaxy with different geometry. And what happens is that hydrodynamically, the outflow propagates along the low density channels through the galaxy. And once it reaches the scale height of the galaxy, it breaks out into the low density halo. It's a purely hydrodynamic effect. And then at the end, you see these bubbles, right? So we see that bubble over here, and you should imagine a symmetric bubble on the other side of the galaxy. These bubbles have, of course, been seen. Starburst galaxies make them. Fermi bubbles, people have heard about Fermi bubbles. That's a similar type of phenomenon, except 4 or 5 times less powerful than in quasar feedback. And so the point that I want to make here is that what we see critically depends on the geometry of the galaxy and on the density distribution of the stuff in the galaxy, and much less critically on exactly how the outflow was launched or what the original geometry of the outflow was. And so this ISM, this phenomenon is multi-phase. We see low density gas, high density gas. It requires multi-wavelength probe across the wide spectral range. Quasar feedback was a theory for a decade. People postulated it, famous semi-analytical models were written about it, but basically there were 0 observations of this phenomenon until 2008. And then people started developing techniques for doing this. And so I spent about a decade kind of developing some of the early and sort of later techniques for doing this. So keeping in mind that the density distribution and clumping is crucial, you have to have different probes of different phases. And so I grouped them. So I did this work with a bunch of postdocs and graduate students and undergrads. I'll show some pretty pictures that I'm not going to walk through, but I grouped them by sort of 2 groups. The green box shows the methods that a lot of groups use, that methods that are very well developed. So for example, warm ionized clumps can be probed by emission and absorption lines, and I will show James Webb observations that are exactly that method. And so similarly, cold and neutron molecular phase can be probed by emission and absorption lines. I just told you about superbubbles. Several groups have observed superbubbles from quasars. And then these orange techniques are personally my pet favorite. So those are the ones that have been developed maybe within the last 5-ish years. And so there are not so many people working on this. So we were kind of new in this field at the time. And I'm very happy to talk to people in detail about this because I'm very excited about this. So it's a hugely active area of research. Even before James Webb, there was a huge community working on this. But one thing that remained, so I would say that the winds, quasar-driven galactic winds, were detected before James Webb. They're perhaps not super beautiful pictures, but they were detected. The problem is that they were, it was unclear what they did to the interstellar medium of the host galaxy. And so the exact mechanism of how quasar feedback affects galaxy formation is very much a James Webb question, which I think is being resolved now or will be resolved by James Webb observations. So that's how we came into
Nadia?
it.
Nadia, are you going to tell us what spectropolarimetry is?
Not in this presentation, but I can give like a whole other presentation about it. I mean, very briefly, okay, so it's an interesting, unique technique to probe the geometry of the quasar on scales that cannot be probed by any other methods. So if you have a quasar, it emits photons every which way. And so if you have some geometry, circumnuclear geometry of the gas, this gas will scatter the photons, and then these photons will arrive to the observer, even if those photons wouldn't have otherwise arrived at the observer. Scattered light is polarized, so when you take spectra in polarized light, you can capture this component. And so it turns out so for example, if the scattering medium is moving relative to the original quasar, then you can capture the kinematics of this movement, and you can learn something about the structure of the quasar on small, on the scale that you cannot possibly resolve by any instrument. And so we wrote a bunch of papers on this. It's a very observationally expensive technique because it's a very weak, fractionally very weak signal. So it is only accessible, from Keck, for example, on the ground. And so but there are a couple of classes of quasars where you can learn super interesting things about it. So, but otherwise, I'm afraid that I don't think I have slides.
Okay, so that
for
was
this.
great. Thank
Thank
you very
you. Thank you for your question. This is definitely one of my favorite techniques. And usually in any audience in any conference, there are about 2.5 people interested in spectropolarimetry. So I say the word Stokes parameters and everybody's eyes glaze over. And sometimes I do meet this other second person who is interested in spectropolarimetry. Okay, so with James Webb, we got involved pretty early on in 2017. I had a postdoc, Domenico Wilazalik, who's now professor at the University of Heidelberg. So early release science programs for Webb were designed so that there would be community effort to develop software for a scientifically useful analysis of Webb data. And so I was not excited about this because there was a software component to it. And I did not want to take on a big software project, but she did. And so she led this program, and we are now all grown up. We have a pip installable package, and we have read the docs, and we have a package that people are using and that we're using for the analysis of integral field unit observations of quasars. So integral field unit, again, a spectrum at every point in the field of view. And what we're trying to do is we're trying to do high contrast observations. So you have a super bright quasar, very faint host galaxy, and you're trying to learn something about the host galaxy. You need to decompose this emission somehow in some clever ways, which is what this package does. So one of the things that was a little bit shocking to me when I started working on Webb data. So Webb takes a while to slew and set up and start observing. So there's a lot of overhead involved. So it's not at all like survey science. You cannot just run around and observe a bunch of, yes.
For this spectral technique, is there a similar pathway as reverberation mapping of using it to find mass measurements of the central object? Can we do the spectral technique at different times in a way analogous to reverberation mapping for the entire light curve?
Okay.
And finding features?
This is a fantastic question. So this is not what we do because we're looking at supermassive black holes and distant galaxies, but people who use this integral field unit techniques in nearby galaxies can absolutely do that. You still have to resolve the quote unquote sphere of influence of the black hole in order to measure the mass of the black hole, right? So you have to find objects that are close enough where your spatial resolution can get into where the black hole is dynamically important. So from the ground, there were some near infrared actually observations which allowed people to measure supermassive black hole masses in some nearby galaxies. I am sure this is going to be a thing for James Webb to do because of its superior spatial resolution. I have not yet seen it done. The reason for this may well be because this is very complicated. So we just got into this early, so we were able to digest all the data, learn how to reduce it, learn how to analyze it. But honestly, the barrier for using IFU data from Webb is very high. It's getting better. The data reductions are getting better and better. You know, it's still very challenging. So for galactic scale things, you do not expect to see significant variability, right? The time scales are not conducive to it. And so it's basically either reverberation mapping or spatially resolved things on much larger scales, but not both, right? Like you cannot, you know, with reverberation mapping, you're probing very small scales where light travel time is comparable to the time scale of your observations. And with these types of measurements, you're probing scales that your telescope can resolve, right? Spatially resolve, like literally make an image of. Okay, very good question. So one of the things that I am still finding a little bit challenging is that with James Webb, you know, you flew to the object and you stare at it because of all the overheads involved. So those are very expensive overhead observations. And so oftentimes you will see papers publishing, you know, one object or sometimes even one line in one object at a time. And so for me, coming from survey science, that's very challenging. And so what I see the field doing in the next few years is now we have had a little bit of time to digest the techniques and the data. Things are definitely going to be transitioning to statistical and populations work. Okay, so let's talk about the actual data. So this is our James Webb data on an extremely red quasar at redshift 3, 12 gigayears ago. It's likely a super Eddington quasar. I have a whole other thing about super Eddington quasars that unfortunately I don't think I have time to talk about today, but it's one of the most luminous quasars at its epoch. We already suspected that it had extreme galactic winds from the ground-based observations, and so this is the image that we obtained in July, 2022. So one of the first thing that we saw, so this is all made in one particular emission line, 03, redshifted to the near infrared. And so what's color-coded on the top right is the gas clumps color-coded by their velocity relative to the object. And so what you see is the red stuff that is redshifted relative to the object by 700 kilometers per second to the blue stuff that's blue shifted by several hundred kilometers per second. And so this is not containable by galaxy potential. So this is a swarm of gaseous satellites of the galaxy with a velocity, with a spread in velocities of about 1,000 kilometers per second. So the best idea we have come up with a source is that it's a protocluster environment, but even that doesn't do it because if you run it through some basic clustering models, you still don't get to these high velocity dispersions at these redshifts. And
Can you
so,
remind me of the redshift again?
this is redshift 3.
Okay.
And so it's not crazy because people have targeted luminous quasars and radio galaxies before and did find that they are in fact in significant overdensities. The best picture we have for this source is that it's a two systems likely in the process of merging, so it's contributing to the overall velocity spread. And we have a new program to get the redshifts using the GRISM data across the entire field of view to actually measure the mass over density at this redshift. So this would be a very high redshift protocluster. This is, after another few months of reducing and re-reducing and re-reducing the data. This is after removing these satellites and after removing the quasar emission, you see this gaseous galaxy, which is clumpy. So it's likely forming stars. It's a clumpy star-forming galaxy. Okay, what do we actually do with James Webb? So we obtain spectra that look like this. And so you can see that in the spectra, we have a couple of flavors of lines. So we have lines that are very broad. And so these types of lines, when they are showing in permitted emission line, quantum mechanically permitted emission lines, They are likely originating in the black hole sphere of influence. So this is gas moving with several thousand kilometers per second. That's close to the nucleus. Fine, that's stuff that we need to subtract to find out what's happening in the galaxy. And so these narrower spikes are forbidden, quantum mechanically forbidden lines, cannot originate in the nucleus. And those are the lines that we're studying, and we can measure their velocity dispersion, shape. You can see that they have all these funny shapes with like blue wings on this side. So there is a lot of information in that shape, actually. So that actually tells us that there is a gas in hundreds of kilometers per second worth of outflow. So we can make pictures that look like this. On the left, you see the velocity field. Red stuff is redshifted relative to the quasar. Blue stuff is blue shifted relative to the quasar. And on the bottom right, I have an artist's impression of the picture that I want you to have. So it's a galaxy with an outflow, and it's tilted so that the bottom is slightly moving towards you. So that gives it the blue shift relative to the quasar. And the backside is redshifted. It's also actually obscured by the intervening gas in the galaxy, and we see that in the data. So this is, 10 gigayears ago, the wind, galactic wind produced in this host galaxy on many kiloparsec scale. So this is encompassing the entire galaxy. So the quality of this observation, so we had some hints from the ground. I don't even want to show you the ground-based image we had for comparison, because it's like a blob of blue shifted gas. But so now we can do this in excruciating detail, but that's not all. So the most interesting to me piece that came out of this observation is actual physics that we can do for the first time at cosmic noon. And so this is in this image, which is showing the line ratio O1 to H alpha. It's what's called a shock diagnostic. So O1 is a line that's strong if you have a quasi-neutral medium and you blast a shock through it. And so what you see is that where the quasar, again, so keeping this cartoon in mind on the bottom, the quasar illuminates this gas along the kind of north-south direction, and everything is fried within the quasar radiation field. So none of the, O1 does not survive, and so O1 to H alpha is low, and that's shown in the dark, so in these white contours and in the dark red color over here. Okay. Now, where the gas is protected from the quasar radiation field, we can see that this ratio is high. We can also measure velocities here, and we can detect that the velocities are high as well. So this is a big deal. 10 years ago, when I was talking about quasar feedback, people at the conferences would be asking me, well, there's no direct evidence for shocks driven by quasar winds propagating in the host galaxy. How do you know that they do anything? How do you know that they do any damage to the host galaxy? So this is it. This is the direct evidence for shocks propagating in the host galaxy. And so again, hydrodynamically, shocks propagate anywhere where they can find low density regions. And so they're not necessarily obligated to go the same way as the radiation. Radiation can only go straight where it's unobscured. And so you get this mismatch in geometry between the shocks and the radiation that people have also looked for a very long time. But this shock diagnostic off ionization axis is really important in galaxy formation, because it provides us the first direct evidence that the quasar-driven wind is doing some damage to the host galaxy.
Is that roughly your field of view?
Yes, it is our field of view. So this
And
is
it's a few arc seconds.
3 by 3 arc seconds in near spec and a little bit more in Miri. Yeah.
You see lots of H1 here?
Do we see lots of H1 here? So we have no, okay. So we have observations of Balmer lines. We can use them to try to figure out how much star formation happens in this galaxy. It is all confounded by the fact that the quasar is also doing the ionizing, so we have to be careful about this. And so there are protected regions, again, where the quasar is not blasting the galaxy. We can sort of assume that whatever H alpha emission we have from there is due to star formation. So we can get some handle on star formation rates from Balmer lines, and it's a few hundred solar masses per year. It's only an estimate though. So we have I'm trying to think of what else we have, but you know, we wouldn't have anything like 21 centimeter or anything like this for an object like this. We do have molecular line observations.
Yeah, I'm more interested to know whether there's like cold gas and H1 and the star formation is low or high.
Okay, yeah, so so in parallel, and again, I'm not gonna talk about this, but for these objects, we have some CO observations. So we can also do kinematics of molecular gas. Molecular outflows, quasars do launch molecular outflows. They look very, very strange. It's almost like nuggets that are moving with high velocities away from the galaxy. So we have a few papers on molecular outflows, but honestly, I'm still very confused as to what we should be looking for as a signature, as an unambiguous signature of quasar-driven molecular outflow. So that's been very challenging. I could say more. We have molecular hydrogen observations, also very ambiguous.
That's a system that's actively forming stars or quenched?
This is a system that's actively forming stars. It's not crazy for its redshift. It's actually fine. You know, it's kind of like for a massive galaxy at this redshift, that's kind of vanilla star formation.
So the AGN feedback didn't shut down the star.
Not yet. So there is, you know, I have written many papers on this particular class of quasars. We have reason to believe that they're relatively young from other lines of evidence. Yeah. Okay. So okay, I'm going to skip this. Even though it's a movie, but I'll skip it. Let me quickly tell you about our search for dual supermassive black holes at cosmic noon. Okay, so what's a dual supermassive black hole? So suppose you have a galaxy merger. Each comes in with its own black hole. So first they're well separated, and then the galaxy merges, and now they are within the same remnant, the two black holes. Okay, now they're sinking to the center by dynamical friction, eventually form a binary, which hopefully one day we will detect using gravitational waves from these binaries, and then they merge. Okay, so we had this novel technique, which is called variability-induced astrometric noise. So imagine that you have two quasars separated by, let's say, a few hundred parsecs. Nothing is moving anywhere, right, on human time scales. This is way too far for them to do any orbital motion on any relevant time scale. So they're sitting there in the same galaxy. Okay, but quasars have this variability. They just vary stochastically at the level of a few percent or 10%. And so if you see this from the ground, let's say, as one object, you know, what happens is that the photocenter of this joint one object actually moves ever so slightly. And it turns out that Gaia can detect this. It's absolutely fantastical, but Gaia can detect these objects. And so this was a technique developed by my former PhD student, Shanqi Huang, in collaboration with a group at the University of Illinois, Yue Shen and Xin Liu. And he was the one who made this acronym, Varstrometry for Dual and Kiloparsec Scale AGN, VODCA. So if you look on ADS for VODCA papers, that's us. Also, when your student can make up an acronym like that, you know they're ready to be launched in the world and graduate. So it's an amazing technique, and we this is what this technique popped up. So this is as a function of redshift. And projected separations, our points are the red points over here. So you can see that basically at all redshifts, those are the smallest separation dual quasars that can be found. So eventually these two objects will get to the center, start doing song and dance, and emit gravitational waves, become a binary, hopefully merge, although there are many, many, many uncertainties in this process. But those are, you know, very massive black holes. Those are 10 to the 8 and above solar mass black holes that are progenitors of binaries that are producing gravitational wave background that may be seen already by the pulsar timing arrays. Yes.
Go ahead.
No, go ahead.
Can we distinguish quasars from possible high energy outputs like jets? Could there be anything else?
Very
that-
good. Oh, fantastic question. So when we first put this technique together, so we looked in the space of like this variability. This astrometric noise Gaia has several parameters that describes, right? The Gaia has these solutions, right? And then they present like, okay, what are the errors on these solutions? Quasars are expected to just sit there, you know, not show any proper motion, not show any astrometric noise, not show any parallax. And so there's a bunch of flags that can be raised if something funny is going on. So we looked in the space of all those parameters, and we found something that was showing, you know, so we found a whole bunch of blazars using this technique as well. But they separate out from this population in a space of several different parameters. So once you put all of those into account, plus if you have multi-wavelength information, right, blazars are pointing straight at you, they will have radio, they will have x-ray, they will have something, you know. And so we actually have a catalog of blazars if somebody wants them, right, from this technique, but they do separate very nicely in the space of certain Gaia parameters. But yeah, so that is a contaminant, but not a very unpleasant one. Okay, so this is an example. This is a Sloan image, ground-based data. This is what we saw with HST. And then, so, you know, single source appears as a double source in HST. And then with James Webb, we see the host galaxy of this object. This is zooming in on this host galaxy. So this is again the velocity field of this galaxy. It's a surprising observation on several different counts. But again, the cartoon I want you to have in mind is that it's a single disk galaxy. I don't know if you can see this very well, but it's an artist impression of, you know, two nuclei over here. Here's our two nuclei. This is after subtraction, so there's some residuals here. This is not physical velocities. And so it's one big, fairly massive disk, you know, in regular galaxy rotation, containing these two supermassive black holes. A very interesting source of contaminants for us are single galaxy gravitational lenses. So again, there's a ground-based data. This is the JWST zoom into this, so you can see quadruply lensed quasar, and even a little bit of Einstein ring, and then the lensing galaxy. So quadruply lensed quasars are fine. We can, okay, fine, quadruply lensed quasar. But when we have two sources, it's really hard to tell sometimes. So we actually spend a huge amount of time trying to distinguish between physical duals and doubly lensed quasars. A lot of ink, virtual ink. Okay, another thing that I wanted to point out is that we also have sources that look like this, that look like single sources to the HST too, but they still show up with a very high astrometric noise. So those are potentially super interesting as much closer binaries. So, and there's very little we can do about it. Even James Webb cannot help us with that. There are lots of really interesting questions here that we can discuss if I can discuss later, but there's this fascinating potential discovery of stochastic gravitational waves seen by pulsar timing arrays, which may be a little high, uncomfortably high for the population of binary black holes that was predicted. And so with this survey, we are very much hoping to be able to say something about the progenitor population of these exact objects that are potentially producing this background. Okay, in like last 2 minutes, I am going to give you a sense of some of the biggest hits from James Webb that are not from my group. So I don't think, I mean, I can answer some questions, but not super detailed questions about this. So but if you haven't heard about this, then I hope somebody will come here and talk about this, because this is some of the most exciting stuff that's come up of the JWST. So curiously massive galaxies in the young universe. So now we are talking about cosmic breakfast. So redshift 10 to redshift 20, the prime sort of science area for James Webb. And so as I talked about before, you expect to see very strong intergalactic absorption, basically affecting all of the wavelengths up to Lyman alpha at that redshift. And so the expectation is nothing as a function of redshift, and then some flux at as a function of wavelength, and then some flux at longer wavelengths. So the way that people estimate the redshifts for these targets is using these photometric models. And so some of them are pretty iffy, and there's a very strong degeneracy between some templates at high redshift and some templates at low redshift. So here you would be hard pressed to sort of do chi by eye and distinguish the significance of several of these fits, but the solutions are 5.5, 5.1, and 13.5 for the redshift. So they're really different. And so some of these photometric redshifts are very convincing, some are very controversial, but this is now moot because there are definitely some absolutely rock solid spectroscopic redshifts for some of those targets. So finding even one galaxy with age greater than age of the universe at that epoch, or mass greater than the most massive halo, would be very problematic, right? That would break the universe. Okay, so what's actually happening is that people are finding more of these massive galaxies as a function of redshift than anybody had ever predicted. So this is a slightly older plot. The newer plot is like hovering right above the Baruzzi line. And Baruzzi line was not a prediction, but some extrapolation from earlier epochs. But you can see that all of the physical prediction models were over here. And so Baruzzi et al. Was the only one in the right ballpark. And even that actually with the newer observations, even that is a little bit short of what is being observed. So there's not yet been any detections of a galaxy that would break the universe, but it's clear that what's happening is that there's a completely different mode of star formation at these high redshift from everything we'd ever seen before. So that's really fascinating. Another big puzzle that's come out of JWST observations is whether young quasars require supermassive seeds. So let's take a look at this plot over here. So here you can see redshift 6, and this is black hole masses of, 10 to the 8, 10 to the 9. And so people have for years bounced around these ideas. Well, can we grow these objects by Eddington limited accretion from POP3 stars? And so I want you to sort of draw a line that kind of goes parallel, but a little bit below this blue band. And so that would be Eddington limited accretion that could, in principle, start at 100 solar masses and get us to 10 to the 8, 10 to the 9 at redshift 6. But with new discoveries with Webb, they are becoming very uncomfortably high as a function of redshift. So these discoveries are already quite problematic. This is the discovery at redshift 11. And so even Eddington limited accretion no longer puts you into the 10 to the 2 regime. It puts you into the 10 to the 3 solar mass regime, and that's very difficult to produce with stellar remnants. So they're now talking about star clusters, or if it's sub-Eddington accretion, then it has to be direct collapse black holes, 10 to the 5, 10 to the 6. Okay, if super Eddington accretion can exist and be sustained for a prolonged period, then of course you can grow from lower mass seeds. But it's clear that some exotic processes are needed, whether it's higher mass seeds or sustained super Eddington accretion. It's a very, very interesting discovery.
Eddington there, are you putting on an efficiency factor like a 0.1 in there, or are you assuming 100%?
No, I think so, right. So yeah, so there's a certain radiative efficiency that is assumed for Eddington limited accretion. I don't know actually what exactly is assumed.
But it's not,
It's not one, no. And so, with Eddington limited accretion, you can shove a lot of the stuff into the quasar with a very low radiative efficiency. So you wouldn't necessarily see them as a super bright source. So that particular constraint is not super violated, but the question is whether you can sustain it for enough to really grow it many e-folds. And the last one I wanted to talk about, mention, is the little red dots. These two problems are cosmic breakfast problems. So redshift 10 to 20. This is a cosmic brunch problem, redshift of about 5 to 10. So there's like a zillion of these sources that are point-like, that are red in the red and blue in the blue, if that makes sense. It makes perfect sense when you look at the SED, at the spectral energy distribution. So they are red over here and blue over here. It's a little bit of a puzzle. What's going on with this blue continuum? Several different possibilities. But so it's a very interesting physics problem as to what's causing this blue continuum. But the most remarkable thing about these little red dots is not even their weird spectral energy distribution, but the fact that there's so many of them, right? So it's almost certain that they are supermassive black holes. So they're active nuclei. There are some spectroscopic confirmations, but I mean, look at what was predicted, right? So if we look at quasars, the quasars were predicted to follow, again, our standard luminosity function. Were predicted to be here, and little red dots are 2 orders of magnitude more abundant than the previous prediction at redshift 5. And then at redshift 7, they are 3 orders of magnitude more abundant. So huge number of these objects in some weird, highly obscured state, but with this weird blue continuum. So very, very strange. So there are lots of interesting open questions here. Okay, so let me conclude. JWST, spatial resolution, sensitivity, infrared coverage, and instrumentation are all transformational. Things are completely crazy in extragalactic astrophysics with James Webb right now. So I talked to you about a couple of case studies in our group. So we can study for the first time the impact of quasar-driven winds on their host galaxies directly at cosmic noon, which is crazy to me, given how far we've come in only 10 years. 10 years ago, there were no observations of quasar winds, period. For our second case, we can confirm and characterize dual quasars at cosmic noon. And then there are, of course, new deep mysteries that got revealed by the James Webb data themselves. So high efficiency of star formation at high redshift, high black hole seed masses, and too many red active nuclei. Okay, thank you very much. Yes.
Is it possible to, do we have any constraints on the duty cycle opinion?
For which,
For JWST?
So not really. I mean, there are some, okay, so there are some really basic constraints, right? So let's say in a quasar, if we see a photonization nebula extending out to a certain number of kiloparsecs, we can say, okay, quasar radiation definitely existed here. But it's a weak constraint, right? Because it's in a few tens of thousands of years tops, right? So various clustering, so there are measurements, we don't do them, but there are various measurements that suggest that 10 to the 7, 10 to the 8 years for an active phase for a massive supermassive black hole, 10 to the 8 and above, is a good time scale to use. There are also very interesting observations for lower mass supermassive black holes like 10 to the 6 that they flicker. And that is from the weird state of the hot halos around them that are found in this intermediate transition, cooling, heating kind of situation, where it's strongly implied that, they have to be illuminated, then cool a little, then illuminated, then cool a little. But no, there's not a great, direct constraint other than from the number counts, right? Like, so we can look at the number counts, we can guess how many quiescent objects are at any given time. So, again, that gives you 10 to the 7, 10 to the 8 type of time scale, year time scales. Yeah.
In a former life, I was looking for such double quasars and found nothing. And we were working spectrally. So if you had just an integrated spectrum of that object, like not spatially resolved, can you see in the integrated spectrum that it's a double quasar?
So Yes, one of the time-honored techniques to try to look for those objects was, okay, so if you take slightly more separated pair, then potentially, the galaxy is still, you kind of have a chunk of galaxy that's coupled to this black hole, chunk of galaxy that's coupled to this black hole. And so now they have an offset between their narrow-line regions of a few hundred kilometers per second. So there is a very rich technique of looking for split line objects. Unfortunately, it turned out, fortunately for me, unfortunately for other people, it turned out that the vast majority of these split line AGN are outflows. So those are a single galaxy where you see exactly this cartoonish picture that I showed a few times, and you see one blue shifted, one red shifted wing. There are several objects at low redshift. So when I showed you this distribution, so some of this sea of green points is definitely coming from this technique. So they just painstakingly go through these objects with high resolution follow-up observations to determine whether it's an outflow or a dual. And so some of those are in fact a dual. For our quasars, it's been just maddening how difficult it's been to find the velocity offset between the two quasars. We do expect a velocity offset, it's in a galaxy, it's in a rotating galaxy.
But the
So-
broad lines, I mean, we also looked at broad lines, but broad lines are already multi-peaked sometimes.
Broad lines, right. So for broad lines, that would be much more relevant to the kind of stuff that Andrew and I talked about yesterday, right? So when you're very close to the black hole, when it's already a binary, and you're within the sphere of influence, okay, how does the gas respond to the presence of a binary? So again, there are multiple projects, including with Sloan, actually, to look at the variability of the broadline region to find these periodicities that could plausibly be in the shape of the broadline region, plausibly associated with orbital
But your
motion.
baroastrometry is not looking for periodic things.
Correct.
It's just looking for,
These
and
are-
that you can see
It's looking for
spectroscopy.
Correct.
that.
There are two separate techniques probing completely different spatial regimes. So baroastrometry is only sensitive to scales of 100 parsecs and above, because Gaia has to see milliarc second level shifts, or
But-
sub-milliarc second level shifts, and that turns out to be at least 100 parsecs
Right.
and above. For broadline region, people are looking for periodicities, but that will never be spatially resolved.
That's right.
Yes,
But when you're looking at the baroastrometry, there's photometric variability, and that's why you're seeing a
Correct.
shift.
correct.
If you're, for what Dave was talking about, you can look at the line profile, you can look for periodicity, but is it possible just like, oh, I have two somewhat different spectra, and they are varying in their amplitudes?
So I'm getting to this. So
Right?
I'm getting to the answer to your question. So this object is ridiculous. Like, these spectra are twins of one another. I mean, they are the same mass, they have the same iron excess. They are ridiculously close, and O3 is actually very weak. So we did a very fancy cross-correlation technique.
I see.
We did detect an offset between O3 lines of about 150 kilometers per second. So, I mean, we also have ALMA observations to back this up, so that then they're narrower, it's a little bit easier, molecular lines are narrower, it's a little bit easier to see. But that's what I'm saying, it's been ridiculously hard
I see.
to get a smoking gun confirmation rate. For duals, you expect to see an offset of a few hundred kilometers per second. For length quasars, you don't. It's the same quasar that you're just seeing the image off at two different times, basically, but you do not expect to see kinematic offsets between the narrow-line regions. And so for us, that would be amazing, but it's been very difficult. So in the integrated spectrum, it is completely impossible, especially given what we've seen in the data so far, yeah.
That is more-
In principle, this is a great idea. In practice, we've just been defeated. We haven't been defeated, no, it's just been much more difficult than we anticipated.
Hey, Nadia, can I ask a question from Zoom?
Yeah. Yeah,
Thanks, by the way, very much for that really nice survey. I'm so sorry I'm not there to get to talk to you. The question I had was, there was a paper last summer-ish, maybe last spring, by Andrew King arguing on the case of these massive early quasars that they were, I believe, estimating the mass because they weren't taking into account that the emission was beamed. And I'm just curious what, since you're an expert on these things, what your opinion is of that.
So, we had a whole Aspen workshop, basically talking about the error bars on these issues, on these measurements. And so,
Was that this
I mean,
summer?
yes, just this past summer. So yes, there are error bars, but it's really hard to imagine, so these objects at redshift, we dissected these objects in particular at redshift 7.5. So I believe those are UKIDS discovered quasars. I mean, in addition to being complete twins of SDSS quasars at lower redshifts, they're also extremely luminous. So
But
it is
his argument was somehow the interpretation of the luminosity was flawed.
right. Yes. So in my other parallel life, I am studying super Eddington quasar candidates. And so those are these red quasars that I have referred to previously, where we think that they're super Eddington because we have counted up their emission, going into the mid-infrared, for example. And so their emission is very, very high. So these objects are just, their spectral energy distribution is completely normal. I'm not talking about the Myolino target at redshift 11. That is a very strange, JWST only discovery. But I'm talking about these redshift 7.5 objects that are discovered by UKIDS. So they do not look like weird quasars to me at all. They look spectrally in terms of their optical spectra. They have very quiescent looking broadline region for what it's worth, not that we know the dynamics of the broadline region very well, and they have normal spectral energy distribution. So from the, the idea of beamed is a fraught one. So for obscuration can do funny things. You can look down the throat of an opening, of a very dusty opening and infer the luminosity that's much higher. Normally this luminosity comes out at some other wavelengths, for example, mid-infrared wavelengths. So if you don't see a mid-infrared excess in an object like this, then it's hard to, imagine that it's, especially if the spectral energy distribution is so normal and coupled with a very normal looking optical spectrum. So these masses may be overestimated, but they're not off by an order of magnitude, or 2 orders of magnitude, which is what would be required at this point to avoid, one of these more exotic scenarios. You know what I mean? Like their error bars are, half a dex. And I'm not sure that they're even all that biased. They're not 2 orders of magnitude wrong. Like, I think that's the feeling we had after dissecting all the available observations for those sources. I don't know, maybe Andrew meant something, a specific object, but these ones at redshift 7.5, those are not anomalous in any way.
I didn't study his paper in detail,
Yeah.
but I think that a corollary is that over even at much lower redshifts, it could be that there's a systematic redshift dependent mistake in our interpretation of the masses. Overestimate masses, if you assume that the, based on, there's, correct me if I'm wrong, but the cases where we have some direct measurement of the mass of these things are really very small. Isn't that right? Maybe.
Yes. So, okay. So how it's done is in local universe, we have reverberation mapped quasars, or not necessarily in local universe, but you need relatively low mass black holes to vary on relevant time scales. So that's one limitation, right? And so there are very few, 10 to the 8, 10 to the 9 solar mass black holes that anchor this relationship. Look, I hear you. I agree with you completely. These masses are not great. But it's also very challenging to imagine that they are an order of magnitude off, because Sloan radiative efficiency is, Sloan quasars, like the bulk of Sloan quasars, like let's say at redshifts below 6, they have radiative efficiencies in the ballpark of 0.1 or 0.2. They have Eddington ratios in the ballpark of 0.1. And so if you break these numbers by an order of magnitude, there are all kinds of other things that go wrong, such as Zoltan argument might go wrong, because you have to agree between the number density of quasars at high redshift, and they grow into quiescent black holes that we see today. So there are some kind of global constraints that if we violate Sloan quasar measurements by an order of magnitude, we're going to have to seriously rethink, these constraints as well. And so I personally never use these black hole mass calibration relationships because I also think they're a little bit off. They're a little bit biased, but I do not think that they're an order or two magnitude off, if you know what I mean. So a factor of like 0.3 dex biased with an 0.5 dex error, I'll believe it. But it's not these masses over here, the ones that are providing the strictest constraint today on the seeds. They are not 2 orders of magnitude too massive, in my opinion. We just haven't seen, any evidence that they are doing anything abnormal compared to lower redshift quasars.
So, Chris is left.
Okay, yeah.
I think we can thank Nadia again.
Thank you.